event that is now generally referred to as the Great Evolution Wars. And that's a time in Kansas's history, we're in Kansas again, where the State Board of Education decided to redefine science, taking out the stipulation that science use methodological naturalism, which means that it be testable. So they took out the requirement that science test things, which kind of takes the scientific method out of science. What? So I became really interested in how people view science, not just in Kansas, but there's constantly bills similar to the one that has gone through Kansas. There's actually been more than 20 anti-science bills proposed around the country this year alone. So I have a lot of interest in why people look at science and how they think about it. And really, in America, we suck. So there's a survey that goes around every couple of years, and it's called the Science and Engineering Indicators. And they come out, I think, every 4 years. And in the 2008 one, they said many Americans do not give correct answers to basic factual questions about science and questions about the scientific inquiry process. They had another one, obviously, in 2012, but this came out every 4 years. And they had the exact same sentence in here. I just haven't updated my slides since 2010. Yeah, it still works, the same thing. And when it says in here, basic factual questions, I'm not kidding, basic. So here's an example of one. How long does it take the Earth to go around the sun? Shout for me. 365.25 days. Or 1 year, which is the correct answer. It's kind of the definition of a year. You would think that people would know it, but we don't. Only about 62% of Americans get that right. Yeah, we're the smart ones. So go knock it on. You're smarter than the average American. Which is, it's kind of sad. A lot of places this is a D, but a lot of places 65 and under would be an F. And it makes me really sad to think that America fails science. But I'm going to give them a pass on this one, because how many people really concern themselves about the definition of a year, except when they're making their New Year's resolutions that they're not going to keep next week? But what if it's something important? What if it's something that affects your health? So true or false, antibiotics kill viruses as well as bacteria? Good job, that is definitely false. Biotics is specifically speaking about bacteria, and less than half of Americans get this, or barely half of Americans get this right. Which is really dangerous when you think about it, because there's people that get prescribed antibiotics all the time and they don't understand the science behind them. So they go, oh, I feel better now, I'm going to stop taking my antibiotics. And what happens is you get evolution, and the ones that are left are the ones that have diverged, and they are a little bit stronger. And that's why we have all sorts of strains of infections in hospitals now that we are running out of antibiotics to kill. So I have this really big interest in why aren't people getting this? There are times people do get interested in science, but it tends to be about bad science. I have an entire new panel I just debuted next year. It's not appropriate for an anime convention, but I call it Why Everything You Know About Quantum Mechanics is Wrong. Because Star Trek. I'm not kidding. My intro video to that one is 2 minutes and 30 seconds of all the different instances where they use quantum in all of the Star Trek series. They have over 50 different ways they use it, and barely any of them make any sense. So people get excited about science. I go to a convention called Archon where I did do that panel, and I hear people talking about this stuff all the time. But then I talk to people about real science. I'm going to be giving the Astronomy in Japan panel tomorrow, and I bet there's going to be 10 people there, because that's how it goes. Hard science, good science, people don't get excited about. And that's kind of the big reason I do this panel, is because I want to show people that you can do basic, good science without it having to be wacky. So, saying that, I can go ahead and get started with the panel, but I always do issue my warning. This panel contains algebra, graphs, calculus, scientific notation, and unit vectors. Sorry, I usually have some different ones in there, so I have it memorized differently. But this is my 5-year anniversary, so we are doing a little bit longer of a panel this year. I've included a few from previous years, like I always do. And you'll get to see the evolution, because you're going to see just how much bad resolution I used to have 5 years ago. So we'll start off with this one, concerns gravity. This is something that pops up in tons and tons of animes, but my favorite clip is obviously going to be from Advent Children. I think so, but one, it's Final Fantasy. And two, how are they falling that long? I'm trying to illustrate a point here. But I do want to kind of break that clip down a little bit, because one of the things that they are doing in that is they are falling while they're jumping off all these blocks and other things that are falling down around them. That doesn't kind of work, but I want to start off and kind of simplify that video, because there's a lot of Sephiroth in that video, which I understand is a little bit distracting. So let me simplify this into something that I think there's a little bit less distractions on. So here is my custom animation that I am still amazed that I've never heard back from any animation studios going to want to hire you. One day, Bowser kidnaps Luigi. Mario rushes on the scene to save the day, but Bowser flies off in the sky. Fortunately, bars start falling from the sky. Mario hops up them and saves the day. So we have the exact same situation here. There's falling things, and someone's going to jump on them and then try to jump up them and, you know, get some higher advantage. How about no? So let's go through the math on this one. Whenever you have a body in free fall, there's going to be forces acting on it. There's always forces acting on anything, but it's simple in free fall because you have the gravitational force directed downwards. This is just mg or ma, where g is the gravitational acceleration, so it's the mass times the acceleration. But there is something slowing you down, unless you're, in a vacuum. And that's going to be a resistive force. That's going to be proportional to something that's called a factor of k, m, and v. So you got the mass in there again. How fast you're moving. Obviously, me standing here, I don't have a lot of wind resistance because I'm not moving. And then that k in there is going to be something about how dense or viscous the fluid you're moving through is. So let's kind of just put these things together, sum of the forces. That's a good way to start in physics. So we're going to say the total force is equal to the negative gravitational force because, down is going to be negative. And then we're going to have the kmv in there, and the k is going to be negative just because it's a resistive force. And if you guys know, like some college level calculus, that's also Newton's law F equals ma. We're going to use the calculus version of A, so dv dt. And we just have to say that the resistive force, that k and v, has to be greater than 0, so you know it's actually resistive. So let's play with that with some calculus. I know I've lost most people already. Alright, I'm just going to factor this. This is a high school thing I think some people can follow. There's just an m in there. I'm going to take the m out of the rest. And now if you look at the middle part of the equation and the part on the right, I've got an m on both sides. Let's cancel it. I like canceling. So I did that and then did a little bit of rearranging. You can see that the m's are gone, and I brought the g plus kv down to the right side, brought the dt up to the other side, left the negative, and because I've got all these little d things, I can toss the squiggly things on there, for those of you that know calculus, I'm just going to integrate this, is what I'm doing. And that's going to start telling me how things are going to move. Yeah, this just got complicated. So once I get integrated, I get 1 over k equals times the natural log of g plus kv equals negative t plus c. We want to get rid of natural logs because they even scare me. So I'm going to, make it all to the e power after I put the k to the other side, so I can do that. And now we have that g plus kv equals e to the negative kt plus kc. V is what I'm looking for here because v is telling me about the velocity, the motion. So let's solve for that. And now we have this ugly, ugly thing. But it's not really that bad, because g and k are both constants. T is the only actual variable in that equation. And that little c, that's a constant integration. So there's not really a whole lot to worry about. But what's important here is you see that e is to a negative power, and whenever you have a negative power getting really big, it makes that thing really small. So if we have t getting really large, it's going to start dominating that first term, and it's going to get really, really large in the exponent, which is negative, so that whole first term basically just disappears, and who cares? Which means as t progresses and gets really big, that whole first term is gone, and all you have to worry about is that g over k. Which means that the longer you're falling, you approach a constant speed. This is also known as free fall velocity, or terminal velocity. So that's what this is saying, is that if you have things falling, they reach a terminal velocity. I could have just told you that, but the calculus was impressive and everything. But here's the thing. Notice there's something missing from this equation down here at the bottom, and that's the mass. It doesn't matter if you're Mario, it doesn't matter if you're a steel girder that's orange. It doesn't matter if you're Sephiroth or a giant chunk of a building. You all fall with the same curve like that. There are small variations going to be based on your surface area and your shape, but not a whole lot. What this means is that if you are the second thing falling, so the blocks start falling out from under you, as with Cloud and Sephiroth, you're going to have the same curve as that, it's just going to be shifted to the right, meaning you're not catching up. And if you don't catch up, you can't jump off of it. So, let's redo the Mario clip with how this will really work. One day, Bowser kidnaps Luigi. Fortunately, Mario rushes on the scene to save the day, but Bowser flies off in the sky. Just then, Bars start crawling from the sky. First clip I ever did in this panel. Aww. Alright, jumping forward a few years. This one I think I introduced last year. This is from Avatar: The Last Airbender, the wonderful culture, not the thing we don't talk about. This is from the last episode. This is pretty much spoiler-free, but if you're really, oh my god, spoilers! Cover your eyes, close your ears. I just went to slides, didn't I? Yeah. What's going on is everything's kind of cool now. There was this big, evil, threatening comet that was giving the bad guys power. But, you know, the hero saved the day because that's what heroes do. And he can save that monkey and leave everything. And since everything's fine now, the danger passes and the comet flies by. Shiny. But how many people have seen a comet before? What does a comet look like? Not that. So there's actually a comet that's appearing really, I think it's right after sunset in the west right now. It's pretty faint low on the horizon from here, but there's a comet, and it's just kind of hanging in the same place every night, which means it gets carried across the sky over the day where we can't see it, but you know, other parts of the world might get to. But it doesn't move across the sky like that. While comets are moving very, very fast, they're also very, very far away. It's like watching a plane on the horizon. They're traveling 300 miles an hour, but they're just... So comets shouldn't look like they're moving like that unless they are very, very close. So when I saw this clip, I'm like, man, how close is that thing? Can I math that? Why, yes, I can. So let's start off with a again simplified diagram. The ground is green, the sky is blue. I am here and so are you. We have a black line just so I can start drawing some triangles here because triangles rock. I can't get a really good feel for this video because there's not enough reference stuff, but what I kind of estimated here is that the comet starts off somewhere up here-ish at about 45 degrees. And then it ends off at the end, it starts off about here at 30 degrees and it ends off pretty close to the horizon at about 15 degrees. So I draw in those two lines of sight. That's not a triangle yet, so let's complete the triangle by drawing a line parallel to the ground. Alright, so we got that. Up in the upper left, we have that angle is 15 degrees because alternate interior angles are convergent. And because this is a flat triangle, we know that the total sum of the angles is 180. So now I know that one's 135. Yay, figuring things out. But that's not what I'm looking for. I want to know how high above the ground this comet is. So let's draw in a thingy over there. We'll call it H. And then we might also need that D, so I'm just going to give it a label in case I do need it. I'm not sure what I'm doing yet. Then some other information. Comets travel about, 50 kilometers per second. That's really, really fast. So a kilometer is like 2/3 of a mile. So 2/3 of 50 miles is something like 35 to 40 miles per second. Yeah, you'll get a ticket for that one. So in 3 seconds, which is how long that clip was, the comet would have traveled about 150 kilometers. So that gives me some information about that side up there. So now I can use the law of sines, which is pretty cool because it's one of those things that I use and then I never ever remember how to use it, and then I'm like, oh my gosh, I get to use the law of sines, that's cool. I guess my life is different than yours. So law of sines, we got the 150 is going to, over the sine of 30 degrees is equal to the d over the sine of 135. So a sine in its opposite angle, and the sine of it is equal to another one. So that gets me D, which tells me that the distance along the line of sight at the end of that clip is about 210 kilometers. That's pretty close, but now, since I got the D, and I know that 15 degrees, I can use some SOHCAHTOA, yeah baby, to figure out what my H is going to be. Since I know D now, plugging that in, the height is going to be 54.9 kilometers, roughly, which is really, really low. So let me kind of put this in context here. Off to the right here, here's kind of an example of going up. So at about 6 to 20 kilometers, that's where planes fly. Mount Everest is only, I think, 3.2 high overall. Weather balloons, they don't even get to 50 kilometers, they're 30. Meteors, they burn up in our atmosphere around 70 to 85, and then the auroras, they're hitting the very upper atmosphere at about 100 kilometers, and the shuttle's maximum is about 300 kilometers. Not that we have any of those anymore. Sad panda. So where's the comet again? It's way down here where meteors are burning up. That's kind of scary. Especially because there's this meteor that's going to be passing in 2029 and people are freaking out about it. How many people have heard of this asteroid 9924 Apophis, or the Doomsday asteroid, or one of those things that constantly goes around in those spam emails? So a lot of people have heard about it. Are you hearing good news? No. Oh my gosh, we're going to be hit by an asteroid and dinosaurs. Oh. Yeah, we're going to go the way of the dinosaurs. No. We've got this thing's orbit figured out really, really well right now. So you see the path of the asteroid there, it's kind of that fainter blue line, and then that white line perpendicular to it is our 99.99% confidence interval of where it's going to be. And you notice it doesn't touch the Earth. But the distance between the Earth, that little dot, and blue line, this is all the scale, is 40,000 kilometers. So if you scoot that line over, so instead of 40,000 kilometers, it's 50 whatever, the marginal uncertainty would mean you should be panicking a lot. Especially because, our atmosphere goes a little bit beyond there, and bad things happen when things enter our atmosphere doing that. I don't know if you heard about this a little while ago. There was a meteor in Russia. So they're looking at the smoke trail, and then all of a sudden, oh snap! I don't know if anyone knows Russian, but maybe I should have had an 18+ warning on that, I'm not sure. So what happened there is this asteroid came into our atmosphere, traveling at supersonic speeds, and the shockwave from that blew out thousands of windows, hurting over 1,000 people with debris and stuff like that. They've kind of traced back how big that asteroid would have had to have been to do that, and it turns out it's about the size of an SUV. That's pretty darn small. Comets are about the size of a city. So if they're coming into our atmosphere, and comets travel faster than asteroids usually, imagine what's going to happen there. I don't want that coming anywhere near us, not just because I'm panicking, because if it hits our atmosphere, it can go exploding. So when I was getting set up, somebody told me that there needed to be explosions if I'm going to call this anime Mythbusters, so I'm going to reference it, but the hotel and OPCC won't let me do explosions here. Otherwise, I do have a segment that does feature them. So going on, one of the first segments I ever wanted to do in this panel was talking about blood pressure in anime characters. And it took me forever to figure this out. In fact, I just solved it a little over a year ago, and I finally included this in the panel last year. I had searched far and wide to find a really good clip. It's ubiquitous in animes, but finding a really good one that made me giggle took a while. So here's a fun clip for that. So how can I describe this? Well, I finally figured out I can solve this by considering work, the idea of using a force over a distance. So there's a couple different kinds of work that get involved here. So you have a change in pressure. Work has to be done there. So you have an equation for that, is that the work done by the pressure is equal to the change in pressure, P1 minus P2, times the volume. So what the volume of the canister doing the changing is. So in this case, the P1 would be the blood pressure, the internal pressure, and another P1, that shouldn't be a P2, should be the atmospheric pressure. There's also work being done by gravity, by lifting all that mass, whatever distance it goes, and and that's an easier one. That's just mg, h, or h also being the change in height, so y2 minus y1. So we can set these equal because work is generally conserved. And also, I do need to say that the mass is going to be equal to the density times the volume. So putting that in there, I get that the work for gravity is rho v g times the change in height. Now we can set these equal, and that's yay. Because again, just like in the very first segment, we have two things on both sides of the equations and we can cancel them out. So goodbye, v's. So now I have something about the change in pressure and a whole bunch of variables that I can probably figure out. So I can figure out the P1, that's what I want to know, the internal blood pressure there. It's going to be equal to the atmospheric pressure times the density of blood, which is basically the same as water, the gravitational constant times the change in height. So let's look at these variables here. The initial height, thing always in physics, and this is one of the things I love about it, just call wherever you're starting, that's 0, whatever. So if I get a cut on my shoulder, that's 0. And how high is the blood going to go? Well, I don't have a good clip of that has a nice meter stick right next to it that I can easily reference. But it does tend to seem to spurt out at a pretty consistent rate. It seems to go about a torso length in one frame usually. So I can figure out from that the velocity of the blood has to be about 15 meters a second. So from that, I can plug that into a height equation to get the total height the blood is going to reach, if that's the case, should be about 12.5 meters, which is really tall. But the atmospheric pressure also, it's about 10.1 kilopascals. Again, the density of blood is the same as water, and the gravitational constant is, of course, 9.8 meters per second squared, negative because it's down. So if you plug all that in, we get that the blood pressure of an anime character is about 224 kilopascals, which, okay, this is one of the things that I always have a pet peeve about other science things. Yeah, we're going to give you some numbers and units, and unless you work in the field, you're like, what the heck's a kilopascal? So let me try to really put this into context. The average human's blood pressure is about 12 kilopascals. So we're about a factor of 20 higher. When I first did this panel, this was actually a suggestion someone and I had been wanting to do it, but they phrased the question when they asked it at the end of the very first year. They said, why is it that an anime character has the blood pressure of a soda can? Nailed it. Alright, so moving on to the Pokemans, I choose them. So first off, what is up with a Pokeball? It does this thing where it hits something and then it goes all glowy, and then it turns into this weird shapeless blobby line kind of thing, and it's captured. So I have to try to figure out how do I want to rationalize this one. But there's two things I see out of that. First off, the Pokemon doesn't have a cohesive form. It's not just being shrunk down, it turns into that weird light beam that's stretched out and distorted. So it can't have a cohesive form. Second off, it can't have mass anymore. Because imagine you capture a 500-pound Onix, stick it on your belt, and that makes no damn sense. So how can I explain this? Well, we could just disassociate the Pokemon, break them into constituent atoms, and that could, make them funny shapes, but it still has mass. So the only way I can see a Pokeball working that satisfies both of these conditions here is by converting the mass to energy. So this is the wonderful, famous equation, equals mc squared, but we're going to need some constants to plug into that. So I'm going to use Pikachu because Pikachu is so iconic, and according to the Pokedex, he's 5.9 kilograms. The size of a Pokeball, it's about this big, so about 2 inches across, which means the volume of it is going to be 5.2 times 10 to the negative 4th meters cubed, so not a good sized living space. We want to, as I say, convert that mass to energy. So we're going to use the equation equals mc squared. We got Pikachu's mass right there, which means Pikachu's worth about just under 2 billion joules worth of energy. Again, units and scientific notation, so we need some context here. And that's why I did the thing with talking about the size of the Pokeball, because that's a lot of energy in a very small space. When you have energy bouncing around, it tends to heat things up. So let's ask, how hot is that Pokeball going to get? So what we want to do is figure out just how many molecules of air there are in the Pokeball to spread that energy amongst. In a cubic meter of air, there's about 3.4 times 10 to the 25th molecules of air. So in that smaller Pokeball, you're going to have about 1.8 times 10 to the 22 molecules. So then you can use the energy equation where the energy is equal to 3 halves kT squared. We have the energy, we have K because it's a constant, so we can figure out T there, which means the temperature of that Pokeball is going to be 4.8 billion degrees Kelvin. Let's put that in units I think everyone else understands. So I'll just leave it in Kelvin because after actually you do the conversions to Fahrenheit, it's pretty much the same, and that's a big number. Who deals with billions on a normal, everyday basis besides astronomers? Temperature of a blowtorch is only about 2,000 degrees. The temperature of the surface of the sun is 5.7 times 10 to the third. The temperature of an atomic bomb is a little bit better, 3 times 10 to the fifth. The core of the sun is about 1.6 times 10 to the seventh, where it's fusing hydrogen into helium. The temperature necessary to fuse oxygen, if we want to do heavier things that have, more resistance because you got more protons in the nucleus repelling each other, making it harder to fuse, you need to fuse oxygen at 1.5 times 10 to the billion. If we really want to get hot, let's talk about supernovae. 1 times 10 to the 11th. You notice I left a hole there? Because that's where Pikachu in a Pokeball fits. And what was that line right before it? Temperature necessary to fuse oxygen, and what's a major constituent of our atmosphere? Our atmosphere is nitrogen and oxygen. Mostly, nitrogen is even less massive than oxygen, which means that you would be able to fuse our atmosphere, at least temporarily, because it'll expand and that'll kind of peter it out. But either way, capture Pikachu, you destroy the world. You will burn off our atmosphere. So, Pokemon's kind of scary now. But since we were talking about the temperature of the sun, there's another Pokemon that really interests me, and this is Macargo. And according to the Sapphire Pokedex, his body temperature is about 1,800 degrees, or 18,000 degrees Fahrenheit, which again is about twice the surface temperature of the sun, which is a little bit warm. So I want to ask, the sun, I'm a skinny, pasty white guy, and I sunburn easily, so sunburns are something that's always on my mind. So how bad of a sunburn am I going to get from being here in Macargo? So I'm going to take just like a nice round distance. I like round numbers, 10 meters. How bad is it going to be when I'm standing 10 meters away from this little guy? So the first thing we have to understand is how emitting objects are going to emit. So this is a graph for what's called a black body. It's something that is giving off its radiation in a nice distribution. Most things are actually pretty close to this. Something that's really hot is like that top curve there, where the peak is kind of right under the eye and visible. And so that's something like the sun, where it's getting off most of its energy in kind of the yellow-green part of the spectrum. That's kind of why the sun is yellow. So something that's hot is going to be giving off most of its energy there, and then if it's cooler, it glows red. So a stove burner, it glows red because it's hot, but not as hot as the sun. You have other things that are cooler, and then they start glowing in the infrared and then the radio. Humans are not awful black bodies. There's a lot of other physics going on that starts getting complicated, but we do give off most of our heat in the infrared. So where's Macargo on this? Well, as I said, that top curve there is the sun. So you can imagine Macargo being about twice as hot as the sun is going to be way off to the left in the ultraviolet off this chart. And the other thing that's important to notice is that there's a lot more area under the curves as you get hotter. That bottom one there is nice and shallow, so if you kind of look at just all the area underneath it, the total amount of energy it's giving out, it's not so much. But the sun's giving off, obviously, quite a bit, just by virtue of being hot. So I got the equation up there. This one's pretty nasty, and I don't want to go through it. I'll just say that, I plugged in the constants, and I integrated it to figure out what the total energy is going to be. I just did it for the ultraviolet B range, so the 315 to 280 nanometers, to try to figure out just how much UV he's giving off. So integrate over that range, and I get that the Macargo is giving off 6.44 times 10 to the 23rd watts per meter squared per steradian. Steradians are a weird unit. I don't know of any field that uses them besides astronomy. I'm sure there are. So it's just kind of like a volume of a wedge of a spherical coordinate system. But the watts are important because that's an amount of energy, and the meter squared is going to be important here in just a minute, but let's do the same thing for the sun. So we do that for the sun, and we get that it's only getting off 2.15 times 10 to the 22. So really only about a factor of 30 off, which is a lot, but there's some other things to take into consideration. We got the meter squared and the steradian, so let's go ahead and talk about those. So those are these two other effects. McCargo is going to be 10 meters away. The sun is 93 million miles away. So the sun's light is going to get spread out a bit more, where McCargo is going to be a wee bit more concentrated. But at the same time, McCargo isn't that big. The sun is big. So while McCargo's light is going to be more concentrated, it's not giving off as much in general. So let's take those into consideration. So we plug in the values for the two missing pieces there. The distance, which is going to be the distance to McCargo, and then also the surface area of the emitter, and then we figure out that McCargo is really going to be hitting us with 3.22 times 10 to the 21st watts. For the sun, though, 2.94 times 10 to the 15th. Now we are 6 orders of magnitude off, or about 10,000 times more radiation from McCargo. That's going to equal a pretty nasty sunburn. But there's one other thing. Between you and the sun, there's this thing called an atmosphere, which blocks 98 to 99% of the UVB. So we need to actually reduce the amount of radiation from the sun by that factor. And when we do that, we get that the sun's only going to hit you with 8.22 times 10 to the 13th watts. And so if you take the ratio of how much UVB you're getting from McCargo versus the sun, McCargo is hitting you with 3.65 times 10 to the 7th. So just over 3 million times as much. Pasty white guy like me is going to, just be burned instantly. So not the Pokemon I want to go around capturing. The analysis is finally going on to new segments this year. How many people have seen all these segments before? Oh, good portion of you. Thanks for coming back. So this one, Gurren Lagann, because I've never done a Gurren Lagann segment before. I could really do an entire panel just on this series. So this, I think, comes from episode 6 or 7. And Yoko's just going around shooting things. So yeah, she goes around shooting things, and things are just flying in the air that, weigh more than a car, just go flying. Unfortunately, there's this little thing called recoil. So this is actually a very simple one, it's nice and quick. So it's all about the kinetic energy. Initially, those giant mecha had no kinetic energy in the direction that they are kicked by the bullet, but then they pick it up, and in one frame, they go the entire width of their body. So I figure out that they are traveling at about, once they get hit, about 100 meters per second. And I'm estimating somewhere in the range of about 900 kilograms for their weight, which we're going to actually be using in another segment, so stick with that number. So the kinetic energy they gained from getting hit by a bullet was about 4.5 times 10 to the 8th joules, or 480 million joules. Again, let's put it in a little bit more context, because Yoko will be given that same amount of energy in the exact opposite direction. So we can reverse calculate this for her, again, using the 1/2 mv squared, because energy is conserved. And so we plug all that in to figure out Yoko's velocity, and it turns out she's going about 8,700 miles an hour. So how fast really is this? Well, it's pretty darn fast, because when the space shuttle re-entered the atmosphere, it was barely going twice that. And it glows red hot at the very top of the atmosphere where there's not much. So what this means is if Yoko's traveling that speed through the very low atmosphere, she would probably be burnt up a little bit. Don't do that. But staying on the topic of Gurren Lagann, these mecha tend to land and cause earthquakes. talk about earthquakes. So there's lots of different ones. And there's this wonderful system called the Richter scale that kind of puts them all in context. So there's small ones. On the Richter scale, this is a logarithmic scale. The small ones are micro earthquakes. You don't really even feel them, unless you're a really, really sensitive person, but they are recorded by really sensitive seismographs. You get a little bit bigger, you might start noticing it, but it's not really going to harm anything. When you start getting a little bit bigger, you're going to probably notice it, and things might be shaking around. And then if you start getting bigger than that, it's going to be really noticeable and start damaging buildings. So where are we kind of on this scale from what it showed in that clip? Well, things are shaking. I mean, the whole world's not falling apart. Light damage. So I'm going to be as conservative as I can. I'm going to call this a 4. And now that I call it a 4, there's an equation to kind of figure out how much energy it released. Well, a hand grenade is going to release about 1 times 10 to the 5th joules of energy. Is this slide? He said. A car has about 70 miles an hour, 2 times 10 to the 7th. A ton of TNT is 4 times 10 to the 9th, 4 billion joules. A magnitude 4 earthquake is about 6.3 times 10 to the 10th joules. So the atomic bomb, the first one, was 6 times 10 to the 13th. So it is a really large amount of energy that's being released there. So let's ask how fast that metal would have had to have been going to give you that much energy. Again, we can use the same equation we just used in the last one, the K equals 1/2 mv squared. So plugging that in, solving for velocity, we get that this would have been having to go about 3,700 meters per second, or about 8,300 miles an hour. That is just funny that this mech is traveling very similar speed to Yoko's bullets. I hadn't realized that until just now. But again, burning up in low atmosphere, and either way, I don't think it would survive the impact. So Gurren Lagann has some bad physics in it. Speed of a rifle bullet, in another context here, is about 1,500 meters per second, so it's about a little bit shy of 4 times the speed of, or a little bit more than 4 times the speed of a rifle bullet. But speaking of speeding bullets, how about a speeding bullet train? This one comes from Bakano.
Here, grab my hand!
So they're hanging onto a train and they're going so fast that they're almost parallel to the direction of motion. They're almost completely horizontal in a chain of 3 people. So let's look at a little bit of the diagramming on that. There's going to be some forces acting on it. And what we want to know is just kind of what's that force in the x direction, because that'll let us know how fast the train is moving. Well, I know that they're hanging down very close to horizontal, so I'm going to call it about 5 degrees. I can figure out the force in the y direction in here at least, because that's the gravitational force. So the force in the x direction is going to be another type of force that has to do with how fast I'm moving through a fluid here, so I can calculate that here in a minute to get the velocity, since it has that in there. And the force in the y direction is, again, just the weight of whichever person it is. So we'll only take one person in consideration. And kind of solving everything, I'm trying to eventually work to have V solved here. Here's some of the constants I'm about to plug in. This is a weird way I did this, why did I do that? But we have that the velocity is about 530 meters a second, or that train would have had to be going about 1,200 miles per hour. Not back in the 1930s. Let's even talk about today. The fastest train in the world comes from China. And its top speed unloaded on a straightaway was only 302 miles per hour. So this train from supposedly the 1930s goes about 4 times as fast. I don't see that one working too well. Moving on, Slayer's a nice old anime. Probably one of the first ones I ever saw.
Unless you want to get ripped to shreds, you better come clean and tell the boss where the statue is. Now, where is it?
Okay, Morgan. Here it all comes.
Come on, speak up. I can't hear a word you're saying. I can't hear you!
So the force of her shout physically propels him backwards. She's what? Yeah. But anyway, that must be a pretty powerful shout, and this was again something I've been wanting to tackle for a long time, and finally this year I figured it out. So let's start with, this is going to be the most complex slide I've ever had in this series. Bear with me. So we're talking about a shout. A shout is a pressure wave, so starting off knowing it's a pressure wave, we'll talk about pressure. It's defined as the force divided over an area. Yeah, that gets me a whole lot of nowhere with what I've got going so far. So let's, try to play with that. Force we know is equal to ma, so I'm going to substitute that in. And now that we have the pressure is equal to the mass times the acceleration divided by the area. Well, still, I've got nothing I can work with, so let's play with that a in there. Can I find something that's going to tell me about the acceleration? Well, there's another equation that I can get the acceleration out of if I know something about the velocities. I'm going to need the initial velocity, which is that p v sub pi, and then I'll need their final velocity, v sub pf. And then I'm also going to need the time, and I'm still missing a bunch of that. So let's see if I can find some of those other pieces. I'm going to solve it for the acceleration since that's what I'm going to need, but as I say, I'm missing the final velocity and I'm missing time, so let's jump across and calculate that. So I can figure out the final velocity by how far the guy went from the range equation. How far he went is going to depend on his final velocity times the sine squared times the sine 2 theta, so what his angle was that he was launched at, times divided by the gravitational constant. So I can plug some things in there, solve it for BF, and I get that his final velocity being launched had to have been about 42 meters per second. And that's in the direction of motion, it's not along the ground. But I'm still missing t, so let's see if I can calculate that. Velocity, distance times time. So we know he's going to travel, it looked like about, a couple meters. So if I plug things in there, especially taking some of the other numbers that I had somewhere that I'm not catching offhand, we can figure out, though, that the the time that I'm talking about here is the time that it took the pressure wave to pass past him. So that's where it came from, is that sound travels at 343.2 meters per second at normal standard temperature and pressure. And so with a distance of the width of a human body, about 0.2 meters, the pressure wave would wash over him in 0.00058 seconds. So now I've got my A, I've got my T, I can plug it into the equation here in the center. And when I do that, I get that his acceleration had to be about 13,000 meters per second. So again, remembering that, what's that? You're right, I forgot, I swear I'm a bad man. But remembering that the gravitational constant is about 10, 9.8, we can divide that by 10. So that means he's pulling 1,300 Gs when he gets shouted at. The other thing that's kind of weird to me is we can talk about just how loud this is. We didn't really talk about just what the pressure is. We can now fully solve that first equation. And we get that it's about 780,000 pascals, which is, now we can also talk about what that is in terms of sound, because we all know there's this decimal system. We may not know how to use it, but here's the equation for it. We can calculate that. From that pressure, that would have been about 200 decibels. Hey, guys, is that loud? Oh, please don't demonstrate. I think he's going to tell us.
If you were at the rave last night, you can feel the subs hit you in the chest. We measured it at about 105 dB.
105 for the rave last night. So in terms of just...
For every 3 decibels, it doubles the sound.
Right. Every 3 decibels doubles the actual energy in the sound, because this whole system is logarithmic. It's not, if you double the number, you double the sound. No. It's logarithmic. It skyrockets real fast. So let's also again talk about sound. So a jackhammer, and I wish now I should edit this slide and put in 103 for the rave. 95 decibels is a jackhammer, and we all know how much those suck, especially in the morning. 95 to 100, you will start getting hearing loss if you keep up with it for too long and don't have some kind of hearing protection. A big rock concert is going to be about 115. I guess we don't quite measure up. We'll get there. 125, it's going to start hurting. 140, even just pretty instantaneous ones can start causing long-term hearing damage. A 12-gauge shotgun blast, if you're the one firing it, about 165. And here's a weird thing. Theoretically, the loudest possible actual sound is only 190 decibels, because it kind of, breaks there. So that means that after that time, it becomes a shock wave instead of a sound wave. Her voice was not a sound, it was an explosion. I think this is the last segment I have for this year, and while it's not as intense of a slide as that one there's going to be a lot more math, so bear with me on this one because I've been wanting to do this segment also since before I started the panel. I think everyone's going to know this one. I can't get it. For some reason I decided to rip it a little too large, and when I embedded it, it was all, why are you so large? I can't embed a file that large. V is for bash, right? Everyone's seen Tryman, I hope. I guess my audio is slightly out of sync. So what's going on is there's this magic giant spinning fist thing, and Vash dives in front of it, and with 5 bullets deflects it. It's really odd the way he did it. So I've kind of drawn a diagram here to hopefully it will make a little bit more sense. So originally when I watched the clip, he's kind of running down this line there, and I thought he originally fired before he crossed in front of it, which would have meant that the momentum of the bullets would have actually, steered it down. But in the clip, it goes towards the direction it's up. So obviously he could have only fired when he had just started crossing the horizontal. So here's some starting constants on here. I'm going to figure that this weighs about a small car, so about 2,000 kilograms. I'm going to give it a good distance, about 200 feet or 60 meters. And I'm going to say Vash is like the best athlete in the world. The top human runner runs about 10 meters per second. So he's booking it, because what you want to do is you want to get as far down as possible. So your bullets are going to give it the most kick in the upward direction. Because if you're firing directly down it, you're not changing its course, you're just slowing it. So that's kind of what I'm going to go with here. There's 5 bullets fired, so I got to go through this 5 times. So starting off, the momentum of the fist For anything, its momentum is its mass times its velocity. So figuring out its initial momentum, we can figure out it's going with a momentum of about 100,000. And I'm going to start using unit vectors here because I is going to be in that direction. That's basically saying that's going to be the x direction. I is just kind of another way we call it in physics. So at this initial time, when Bash crosses directly in front of it, the fist's position is going to be at 0, 0 on this coordinate axis. He fires the first bullet. So I've kind of got the momentum of the fist originally. It's going at 50 meters per second. And then he fires the bullet. Well, now we want to worry about the momentum of the bullet. So bullets don't weigh much, but they are going rather fast. So 400 meters a second. So its total momentum, it's going to be slightly off because he's firing at an angle of, if he's moved 10 meters per second, in that 0.2 of a second, he would have moved a little bit less. So he figures that we moved 2.3 degrees. And he fires the first bullet. Its momentum that it's going to hit the fist with is going to be somewhere in there. It's going to have two components to it. You have some, which is the I direction again, so that X direction. It's going to basically push the fist backwards, and then a little bit in the Y direction, so the J unit vector, pushing it the direction to deflect it. Keep in mind, I'm going to keep this whole thing not to scale, obviously, because that's a giant head twice. But at least the center of them is to scale on that background graph. So it's going to add its momentum to the fist, which means that after the bullet hits, the fist's momentum is going to be changed by that tiny, tiny amount. So what's its velocity going to be? Well, now it's going to have a little bit of velocity in the Y direction. But it's still got some distance to travel. So after the next 0.2 of a second, Bash is going to move a little bit more. The fist will move, but because it has now some velocity in that upwards direction, in that time it will have moved a little bit. And so you can see down there at the bottom, it's moved 0.00032 meters in that 0.2 of a second up. So not actually enough to be noticeable on the graph. But don't worry, because that was just the first one, kind of just slowing it down so you have more time, you know. And once he gets further down and starts getting in the right direction, we'll totally have this worked out, right? So we're going to go through the same math again. He fires another bullet. It has the same momentum initially, but because it's at an angle that's steeper this time, it's going to be slightly different. There's a little bit more in the J-hat direction, the Y direction. And now it's changed the momentum of the fist to what I've got down here, changing its velocity to now it has 0.00056. So we lost a 0. Go us. Go Team Bash. So it's sped it up a little bit in that Y direction. So in that next 0.2 of a second, now it's moved 0.0000144 meters upwards. So not even a millimeter. But don't worry, there's still more bullets. Going through this again, faster. So there's its new momentum, there's its new velocity. At the time he fires the next bullet, now it's moved 0.0004 meters. He's still got one more bullet. So now it's moving 0.00283 meters per second in the Y direction. And I think now he's on his last bullet, but now he's got a really steep angle on there. So he's shooting at an angle of almost 50 degrees on, so it's going to get the best kick he can get before things go horribly wrong. So the final number here, when his last bullet is hit, he's out, the fist is at the 0 point, is it's moved 0.0021 meters, or 2 millimeters. Am I missing something? So it's new velocity, not that it's going to matter anymore, couldn't pull it off. So I think that's all the new things I have for this year. It's been a fun hour, so now we can take time answering questions, because that's what we like. We got a mic up here, so if you just want to form a line, that way you can hear, since shouting doesn't work well in a big room. Are you Uncle Iro? Yes. Excellent. I love Iro. Best character in the series.
Thank you. The bullet train.
Yes.